Cosmology. Cosmology is the study of the structure and evolution of the universe as a whole. How big is the universe? What shape is it? How old is it? How did it form? What will happen in the future? Well, the first thing we need to look at is Hubble's law. Every object is moving away from us. So does Hubble's law imply we are at the center of the universe? No, it doesn't. We can understand this by looking at the expansion of a loaf of raisin bread. So here we have a loaf before it rises. And let's just look at all the raisins inside. So these raisins are all situated, and they're not moving through this bread. They're stuck in the bread. Now, as the bread itself rises and gets bigger, because it's rising, every raisin moves away from every other raisin. Not because they're actually moving through the bread, but the bread itself is expanding. Now, as that happens, two objects that are close to each other, the distance between them, this and this, is pretty small. So the distance change between here and here is small over a certain amount of time. Now, the further you are, the bigger the distance change. So I've had a larger distance change between these two than these two. But I've done this distance change, this expansion, at the same amount of time. So therefore, this raisin appears to be moving away from the home raisin at a slower rate than this raisin. So this is what Hubble's law is telling us. The further away something is, the faster it seems to be moving away from us. Doesn't mean that there have things actually moving through the galaxy or through the universe. But what it means is the universe itself is expanding like the raisin bread. So Hubble's law implies that the whole universe is expanding, not that we are at the center of it. And today astronomers think of space itself expanding, not galaxies moving through space. So the raisins in the above example are not moving in the bread, but move with the bread as it expands. The galaxies are not moving through space. Space itself is expanding. So in the early years of the 20th century, astronomers envisioned the universe as a static place with only the Milky Way and a few companion galaxies. It was not until the 1920s that astronomers realized the universe was filled with other galaxies millions of light years apart, and that the universe itself was expanding. Now, no matter which way you look, you see about the same number of galaxies. The galaxies are not spread smoothly, but clump into groups. The smooth clumping implies a similar distribution for the whole universe. Now contrast this with the sky's Milky Way, implying that we are a disc-shaped galaxy. Because everywhere we look, we see about the same, it implies that the whole universe has a similar distribution to what we see all around us. Now in general, a galaxy obeys Hubble's law. The speed of recession is proportional to its distance, the proportionality given by the Hubble constant. Again, the motion is due to the expansion of space itself, not like a bomb fragments going through the air, but like buttons attached to an expanding balloon. If I glued buttons all over a balloon and started blowing it up, as I blew it up, every two buttons would appear to be moving away from each other on the surface of the balloon. Neither one of them is moving on the balloon, it's just the balloon itself is getting bigger. That's the way you need to think of galaxies in the universe. So are we at the center? The recession of distant galaxies often leads to this misconception that we are at the universe's center. However, because space is expanding, no matter where you are located, galaxies move away from you. There is no preferred center. The lack of a preferred central location is called the cosmological principle. So if the universe is expanding, and we know the rate at which it's expanding, that means at some point things were closer together. So let's kind of play the history of the universe in reverse. So we run the universe's expansion backward, implies all mass becomes confined to a very small volume that we call the permeable atom. Now, if we assume galaxies have always moved with velocities they now have, the Hubble's law gives an age of the universe of about 14 billion years. Now, in 1823, Heinrich Ober's offered Ober's paradox. If the universe extends forever and has existed forever, the night sky should be bright, but of course it isn't. Olbers reasoned that no matter which direction you looked in the sky, a star's light should be seen. If I have an infinitely old universe, and it goes on and on forever, then eventually, no matter where you look, there should be a star, and the light from that star should be coming towards us. So the sky should be completely bright with stars. We don't see that. Therefore, we know the universe can extend forever and has not existed forever. Finite age and speed of light means only a finite volume of starlight is available. In other words, the night sky is dark. So what do we know now? The universe is expanding and is filled with very low energy background radiation. The radiation expansion imply the universe began some 13 to 15 billion years ago, depending on the expansion rate. The universe began as a hot, dense, violent burst of matter and energy called the Big Bang. Now, many people consider how the universe started as only a religious question. For scientists, though, the approach is to go out and make observations, what can tell us something about what happened. What we'd really like to be able to do is to be able to look back in time. But we can do this because light takes time to travel from place to place. So light from distant galaxies has been traveling for billions of years. What we see is galaxies as they were billions of years ago. In this way, we can actually look into the past. We can get an idea of how cosmologists can use the idea of looking back in time by considering the controversy that raged in the 1960s between two rival cosmology theories. The rival to the Big Bang was the steady state, which stated that there was no beginning to the universe. As the galaxies move apart, new matter is formed to take its place, so the average density of the universe never changes. The steady state theory had an advantage in that it was more simple. Now, we can test these theories by seeing how far apart on average galaxies were in the past. And as we look back, and this was the present, the steady state should be the galaxies were about the same distance apart in the past. The Big Bangs should say the galaxies were closer together in the past. And when we actually look at the galaxies further away, we see that galaxies are closer to each other in the past. Therefore, the Big Bang theory is the one that fits our model and our observations. Today, there are better tests than this between the two theories, but this is the simplest to explain. Now, when we apply the laws of physics, we actually predict the right amount of helium that we see at present day. Most helium in our universe dates from the Big Bang, not from the stars. However, all other elements were formed in the stars or in stellar explosions. Now, when atoms were first formed, photons were produced. Radiation from this period can still be detected. It's called the primordial background radiation. And we can detect this with special telescopes. The Kobe telescope is one. And we detect it as a faint microwave hiss. And by studying the fluctuations in the background, we learn something about what the universe was like before there were any galaxies. Small fluctuations in the density of the gas in the young universe grow to form galaxies and clusters of galaxies. Understanding exactly how this works is a vibrant area of current cosmology. Now, what caused the Big Bang? That is not a science question, and scientists should not try to answer the what caused it. That is a philosophical question, not a scientific one, because I can never test it. I can never go back and find out what caused it. That makes it in the realm of philosophy. So what about this cosmic microwave background? The proposed very dense early universe implied that it must have been very hot, perhaps up to 10 trillion degrees Kelvin. Now, it was proposed that the universe expanded, and as it expanded, it cooled. That's the ideal gas law. As things expand, as the volume goes up, the temperature goes down. You can figure this out anytime you open a bottle of pop. When you open up a Coke, for example, it immediately gets cold. As the gas that was pressurized in there is released, it cools down in temperature. So, it was proposed that as it expanded and cooled, the radiation that existed at that early time would survive to the present as microwave radiation. This radiation was actually accidentally discovered by Arno Penzias and Robert Wilson in 1965, and has since been referred to as the cosmic microwave background. So very hot gas is going to give off a very high energy light. Say it's blue light. It's actually probably hotter than that at 10 trillion degrees. But now I've got this light coming from between galaxies, and it takes a long time for it to travel. Well, during the time that it's traveling, space itself actually expands. And as space expands, the space everywhere expands at the same rate. And so that blue light expands into a red light. Now, if we actually look at the cosmic microwave background, it follows a perfect blackbody spectrum with a temperature of about 2.7 Kelvin, or just above absolute zero. So current theory suggests that the early universe consisted of protons, neutrons, and electrons. The initial hot, dense state allowed nuclear reactions to create helium. Now, based on the estimates of the early universe's expansion rate, about 24% of the matter should be transformed into helium. And that's in great agreement with what was observed in old stars in the Milky Way and in other galaxies. Now, that's not the only measurement. We can do different measurements on deuterium, which is hydrogen with an extra neutron, and lithium, and all these support the hot, dense early universe theory. The early universe's high temperature and density imply that it had a very simple structure. Mass and radiation mingled in a manner unlike their sharp distinction today. The radiation was so energetic that it easily transforms to mass, and mass and radiation, or mass and light, behaved as a single entity. Now, E equals mc squared tells us that not only can mass be transformed into energy, like is going on in stars, but that energy, say in light, can be transformed into mass. The creation of mass, however, must come in pairs, ordinary matter and antimatter. So, for example, the antiparticle of the electron is the positron. The antiparticle of the proton is the antiproton. This is because we need to conserve charge. Light has no charge. As it comes in, it has enough energy that it can create a particle and an antiparticle. The charge of these two things must be opposite and equal. Now, the same thing can happen in reverse. If I have a positron and electron that come and hit, they can give off light and convert mass into energy, or energy into mass.